All right, so let's do a new topic. Remember, we're doing logic for computer science, and so I want to get as much computer science in here as possible. I have lots of fantastic, well, I think they're fantastic. There is a lot of fantastic logic that comes up in computer science, and I would love to cover as much of it as possible. All right, and we're going to cover some today. All right, so here's Hilbert, and I don't remember if I told you about Hilbert yet, but in 1920 there was a conference in Paris, and he gave a whole list of open problems, and he was so on the mark because that list, each one of them started a whole field of mathematics, which they haven't all been solved, but the ones that have been solved have done great things. Like he asked, what is computation? And in fact, we'll see later, his grad student Turing came up with the Turing machine, right? But before Turing, slipped in a little here, a little, right? He did ask this question in 1920, and Gödel came in 29 and tried to talk about computation from the perspective of logic. And that's what we're doing today is logic, right? So he says, well, no hardware has been built yet. This is all before they had computers. In fact, one of the things that Turing did just a few years later is he built a machine to break the German encryption codes. But that's a different movie. You can watch that movie. All right, so let's talk about computation. So we need various letters to represent things. So let P be a computational problem, right? So P is just, in the logic world, P is just a symbol representing an object. Just like I have G representing a girl, I have P to represent a computational problem. And what is that? Well, P could be sorting, right? Sorting is an example of a computational problem, right? You give me numbers, I sort them. That's a computational problem. And what do we give a computational problem? We give an input. Now, we know that when we're sorting things, the input is an array of values, but computer theorists, they just assume that the input is, what is an input? It's always just a binary string, right? It's just an arbitrary object, and we think about them as binary strings. But up here, I is just another object like a boy or a girl. All right? So what do we want to say? We can think of P as a function, right? P is a computational problem, so it's a function. You give it an input, and P of I then is the required output, right? So here, sort I, what does that represent? Sorting is the computational problem. You give me a list of numbers. Sort I is those same numbers sorted, right? It's the required output. What does it mean for a problem to be computable, right? One of the things that Hilbert asked, and then Turing will answer, is are all computational problems computable? And Turing will say no, some of them are not computable, right? So we have to know what it means to be computable. And what it means is that some algorithm will compute it, right? And what is an algorithm? Algorithm, a machine, is the same sort of deal, right? Here's an example. Insertion sort, you should all know, is an algorithm that I wasn't sure if you can hear me. I had my headphones on it backwards. Anyway, I talked loud enough that that the dead can hear me. All right, so I was just commenting how when I video by myself, I talk very quietly, and when I video with people, I talk too loud. All right, so what are we doing here? We have a computational problem that could be sorting, and then the algorithm is an algorithm like insertion sort that solves the problem, right? And computer theorists, when they talk about algorithms, they tend to think about it being a Turing machine. Why? Because Turing came up with the first model of computation, and it was a Turing machine. But as far as we're concerned, it could be some Java code, right? Doesn't matter. It's something that solves it. So here, A is an algorithm. All we know is it has a finite description. All right, so now what is A of I? Well, it's just what you think. A is an algorithm, you give it an input, and A of I will be the output, right? If it outputs, stops and gives you something, then that will be what A of I is. And if it runs forever, then A of I can say, hey, it's running forever. All right, so what do we want our insertion sort to do? Well, you could have good algorithms and bad algorithms, buggy algorithms, but if our algorithm works, i.e. it solves sorting, then when you give it I, it needs to return the sorted list. Right, everybody with us? All right, so what does it mean for an algorithm to compute, to solve a computational problem? Well, obviously, we need that the output of the algorithm on the input to be as required, right? So we write this as this. This says, I have an algorithm, I have a problem, I have an input. What am I saying is that the output of the algorithm on the input is the required output for the computational problem, right? Everybody with us here? I think we're, all right, so now we know that that's what this means, but Gödel's a logician, right? And so as far as the logic is concerned, oh, here, I did a little dyslexia here. Those got switched, but we don't care that. This is just another true-false relation, a true-false statement. It's either true or false. Here we have various objects, and this is a relationship between these three objects. All right? All right, so now remember our great woman here, she is the one who's going to give us deep insight into what these sentences mean. And so let's try to, this page is a little confusing because different things come into these pages, but hopefully we can put them all together, right? We have different thoughts and we need to put them together. So the one thought is we want to be able to say in English, we wanted to be able to say computational problem P is computable, right? We want to be able to say that. And we want to know what it means. Well, what does computable mean? Computable means that some algorithm correctly computes the problem, right? That's what P is computable means, that some algorithm computes it. Okay, great. Which algorithm? Do all algorithms compute it, right? Or just some algorithm, right? Well, clearly some algorithm. You know, we can't expect every algorithm to compute the problem. We're just saying there exists an algorithm. Problem P is computable if there exists an algorithm that computes it, right? All right, so what does compute mean? Well, it means that algorithm A correctly solves the problem P on some input, right? You have to actually give it an input for these things to do something. So we need an input involved, right? And which input? Is there some special input or all inputs? Yeah, dude, we want it to work for every input, right? Every input. Algorithm A gives you the right answer for problem P on every input, right? Okay, what does solves mean? I just said it already. What solves mean is that algorithm A, you give it an input and it gives you the right answer. It gives you the required answer for problem P, right? So here's our various pieces that we're putting together, right? Now we got to think about the order of these things, right? Do we put the exists first? Do we put the for all I first, exist A? Who comes up with what first? Pretend you're in computer science. You go to your boss. Does somebody give you the input first? Or who gives you the input? Who gives you the algorithm, right? Well, what's our game? What's the devil say here? The devil says, hey, he better give us one algorithm that works for every input, right? We don't want to go over to the Clockwork Orange picture. We want to say there's one algorithm that works for every input, all right? So here's our statement. There exists an algorithm such that for every input, the algorithm solves the problem on that input, right? That's the definition of computable, all right? Now remember, one thing that she likes to do is she likes to start with the inner sentence and move out, and each stage we look at what are the free variables and what does that sentence say about the free variables. All right, here the innermost sentence is just this, and everything is free, right? There's no quantifiers here, so A is free and I is free and P is free. So what is this saying? This is saying algorithm A correctly solves problem P on input I. That's what this says, right? Now let's bring a quantifier in. For all inputs, something is true. Well, what's true? We want to talk about the free variables. Let's focus our attention not on the I, because it's a local variable. It's the A and the P that we care about. And what are we saying? We're saying algorithm A correctly computes P. You know, we didn't even mention the input, right? It's just implied that if algorithm A computes P, it does so for all inputs, right? Everybody follow how we're playing this coming out game? All right, so now we bring in another exist algorithm, and but the free variable is P, right? So what we care about is P. And what we're saying, well, we could say there's some algorithm that computes P, right? We could talk about the algorithm, but we want to give less attention to the algorithm. It's just a little local variable. We care about P. What are we saying about P? We're saying P is computable, right? That's what this sentence is. It's a free variable. If P is computable, then it's yes. If P is not computable, then it's no, right? Everybody get that? Right, so let's review the game. Partly it feels like I say the same things over and over again, but I've been told that the way to teach is to say things over and over again so that you guys can, you know, you can get it. And chances are you're not being bored. Chances are this is all kind of hard. All right, so we play the game, and the blue guy is the prover. He's trying to prove the sentence is true. He produces the exists. And then the red guy is trying to prove it's false. He comes up with the for alls. All right. Now, the reason I'm repeating this here is partly to help you repeating it, and partly I made these slides thinking somebody might jump into the middle of these slides and then they need this. All right. So, and then you win if that inner statement is true. So let's play the game. We go left to right. The prover, that it exists, right? It exists, so the prover has to come up with an algorithm, right? We're trying to play the game to know whether or not P is computable, right? Your boss says, hey, you're in computer science. Prove to me that P is computable. And what are you going to do? You're going to come up with an algorithm that you claim solves P. And then the adversary is going to come and say, you claim A solves P. Yeah, here's an input. Does it solve P on this input, right? I'm claiming this input is a bad input, right? And then the prover wins if A does in fact solve P on this input, then the prover wins, right? And that's computer science, right? That's what we've been doing all along, right? And as I said, P is free, so because it's not quantified, and hence the sentence says something about P. And as you all know, if P is in fact computable, then the prover can supply a working algorithm such that no matter what the adversary does, the adversary can't find a counterexample, right? Everybody see that? This.
I have a question.
Yep.
So, can I limit the input so that the adversary can only choose within a range so that I can win every single time within that range?
Well, you could. The sentence says for all inputs. The classic thing in computer science is we think about I being a binary string and we want it to do the right thing for all inputs. But certainly if we're in a particular field, that if we're in computer science, we could say, we could put some preconditions on the input, right? In fact, we could define the, either here we could limit our inputs to have some precondition, or we could have state in our computational problem that if the required answer, if I equals has some precondition, then we have a required answer. And if I doesn't have a precondition, then P could say, I don't care what the answer is, right? So there are ways of working that in. Any other questions?
Yeah, I have a quick one. I don't remember if I remember you saying before that something about if each input had an algorithm, to think about it like that is wrong. Isn't the statement saying the same thing?
No, no. I'm not saying for every input there's an algorithm. I'm saying there's one algorithm that works for every input. Right here, the prover came up with the algorithm first, and then it has to work for every input.
Oh, okay. Oh, right. Okay. All right. Yeah, that makes sense.
That's the switching of these. We're gonna actually, I brought the, last night, in fact, remember I told you I changed the slides last night. Last night I brought Clockwork Orange Man in because we're gonna be talking about the switching of that again, right? And in fact, what I was just about to say was, it was students in what's the course we're teaching now? 2001. Students, oh dear. Okay, we had a little blip in our recording, but that's okay. So it's sentence like this that people in 2001 weren't getting, that made me so frustrated about logic and made me started teaching logic. All right, so the fact that you can't say for all, if you switch the order here, it says something different. Oh, there he is. I told you I was going to bring him in, and there he is. All right, so you might think I'm recommending this movie. I'm not. It's a scary movie. It's a very disturbing movie, but it was just broke ground for scary movies of its time, and maybe it's still worth watching.
What movie is this?
What? It's called Clockwork Orange.
Clockwork. Oh, okay. Yeah, for a second I thought it was Chocolate Factory because the guy with the hat. I thought it was something else, but then I
well, that Chocolate Factory might be happy. This is not a happy movie, but it still might be worth watching. All right, so so here somebody just asked, what happens if we switch the order here, right? This is the pain, right? This is saying, right, you give me, here's our problem, x squared, right? You give me x, I give you x squared, and what we wanted to be saying is that there exists here's one Java program that solves the problem, right? You give me x, I return x squared. That's one Java program. Well, what this is saying is for every input, there can be a different Java program, right? This Java program gives the right answer when I is 1, and this one when the input is 2, and this one input 3, 4. Here, all of these programs, for each input, there's a program that solves the problem. And we do not want to say that. We want to say this, right? So whoever asked this question about this versus this, I had the same question, and I wanted to stick it in there as a reminder, right? Everybody got that? How are you guys doing for this stuff? We covered half as much time as I wanted. Did we go too slow, or was this all helpful?
I think it's helpful. So
good.
It's okay. Yeah.
I think the speed is fine.
Yeah, I'm really keen on teaching you everything, but I'm really keen on teaching you so you get it. All right, it's now 10:02. We could stop. We could have questions. We could do more examples. This next example here, I got, again, it was a 2001 test assignment at one point, and everybody got it wrong, right? You need to be able to know what I really do believe that if you want to be in computer science, you need to be able to understand what sentences like this mean. and what it says about the relationship between these variables. You guys got any questions?
So this is kind of seeming like similar to the 2001 material that we covered. Is there any like differences? Like I noticed the oracle thing is something we didn't cover in 2001, I think. Are we going to be asked questions about that?
In this course?
Yeah.
Or,
I
yeah,
think
yeah, I'm
we
teaching
actually
you.
cover a little only for the oracle. I remember there's one
Yeah,
slide only.
you were
in
right.
2001.
In 2001, I want you to be able to understand sentences like this. And to understand to understand what the sentence means, you don't need an oracle. So I'm not teaching the oracle in 2001. But in this course, we need to be able to prove things. And we need to be able to prove, well, if A is true, B is true. So when you're assuming A is true, we have to know how we're using the fact that A is true. And so that's where the idea of an oracle comes in.
Okay, so when we are asked questions like this, like to prove something, like if A then B, we would be expected to also say what the oracle's role is in that?
Yeah, absolutely.
Okay, makes sense.
Absolutely. Yeah. In fact, so what we got left on this group of slides is we're going to do a half dozen examples like this, which is just, do we understand what this means? And then we're going to come up with one or two pretty long proofs where we assume a bunch of first order logic statements are true, and from that we will prove another statement that's true. And we'll be playing for all the ones that we're assuming are true, for each one that we're assuming is true, we'll have an oracle to help us, and then we'll play the game to prove that the other one's true.
Perfect. That makes sense.
And it's my belief that this kind of understanding is what you'll need to be able to do this kind of stuff. Later on, we'll do the formal things, and as I say, I personally find the formal things don't have this intuition and leaves people without real true understanding. And so when we get to the formal thing, we're going to kind of map. Took me a while over the summer to understand myself, to understand how the formal thing is sort of saying this informal thing at the same time. It's kind of subtle. So that's why it did take me a while to understand it myself. And so that's how I know that it's not easy.
Would it be a good practice to take like the first assignment that was given to us in 2001 and redo it, but use the oracle to do the proofs?
I don't believe that we ever assumed anything.
Oh, true.
Right?
Yeah.
So there's no oracle. But what you could do is pretend that an oracle knew it was true, right? Look at the statements in that test and say, suppose it wasn't my job to prove it. Suppose it was somebody else's job to prove it to me, right?
Mm-hmm.
Then how would I use that to make my life better, right?
Okay, that makes sense.
Professor, could you go over compile time one more time, just because you talked about like different kinds and it was a little confusing?
Yeah. Here, let's discuss right now. Everybody think, if I drew a law, the game is somebody comes up with the algorithm, somebody comes up with the input, right? That's the game. And you've all done it. You've written computer programs, right? So in the game, somebody gives you the problem, you come up with an algorithm, then somebody gives you an input. And so there's these epochs. Epoch, there's a good word. how would you feel if I changed it to compile epoch? I don't even know what an epoch is. It's a period of time, isn't it?
I think so. I don't know if that'd be better.
I don't know if that'd be better either.
Professor would have to figure out how to spell it before we add it.
Oh,
as a
you
term.
are so right. You know, I don't know how to spell it. I am the world's worst speller. In fact,
Maybe find a
you want me
simpler
to tell
word.
you a little story once? Here's a funny story. I had a roommate, and she used to get so mad at me because I couldn't spell her name. And then I told her, well, actually, I don't know how to spell my name. My name is Jeffrey, and I always forgot whether it was R-E-Y and E-R-Y. And so I told her I always forgot. And then I told her, oh, well, actually, it's spelled E-R-Y. And then I wasn't sure, so I came up and looked at my passport, and I was wrong. It's actually R-E-Y. So I'm a bad speller.
So maybe something similar than epoch.
Exactly. Exactly. But anyway, somebody was asking about this. All right, so we're talking about a period of time where it's after the problem has been stated and before the input has been provided. We're going to call that the compile time, the compile epoch.
So would it be like while you're making the algorithm?
Yes. Yeah.
Okay.
Yeah. So it's not, in fact, the word compile is kind of wrong because you think that it means
Oh, you're compiling
it's
your
while you're compiling
algorithm?
the algorithm, right?
Like
But
you're putting it together?
It includes, yeah, you're putting it together, right? Exactly. You're compiling this stuff for your algorithm,
Okay.
right?
Also, who would be putting it? Who would be making the algorithm? Would this be a computer? Would this be like
Well,
a
well,
simulator,
it's
or would
who's
this be a
ever trying to
person?
prove that it's computable, right?
Okay.
Who's trying to prove the problem is computable is the guy who comes up with the algorithm.
Okay, so it'd be a person, right? Not like a computer.
Well, computers are now more and more coming up with algorithms. So I'm not going to answer that question, but certainly right now I'm thinking about it is the hacker who comes up with the code.
Okay, so the person. Okay.
Yeah.
Jeff, so there are two ways I'm picturing this one, like right now, like I'm translating this one. So over here, two ways. I want you to tell me which one is correct. So there exists an algorithm for every input that gives you an arbitrary number of lines, which is the k, or we can say for every line gives you an algorithm for an arbitrary number of inputs. Which of the two are, which one are?
Well, the first one, did you say that I come up with the input and then I come up with the k?
I said there exists an algorithm for every input that gives you an arbitrary number of lines.
Yeah, I don't like that, right? I don't like that because then that tells me that the k is being chosen after the input. It's chosen during the run epoch, and anything chosen during the run epoch, I'm going to assume depends on the input, right? And I don't want the number of lines of code to depend on the epoch, right?
So and then the second way I said that for every number of lines gives you an algorithm for every input. That's the second way I said.
Yeah. It doesn't matter the k comes first or the a comes first, because it's the same guy. It's the same poor grad student locked in his basement hacking code that comes up with both.
So the second one I said was right. Yeah, the second one was right. Okay.
Yeah. Right.
I have a question about the input. You said that the input is like the k is not dependent on the input. So why include in the relation where you say AI?
Yeah, yeah. We do that because if you want to talk about something that's not, you want to say that something's not true, you need language to talk about it. You need language to talk about the fact, how do I say it's not true? But by saying, here's a sentence that says it is true, and then saying it's not true.
So are they boundaries? Would these be boundaries? So you're less focused on the physical number and more just focused on the fact that it has to be compiled in a finite amount of time, run in a finite amount of time, come up with a solution in a finite amount of time. No?
All right, so yeah, so I like your boundaries and I like your finite. You did do something that showed a confusion. It sounded like you were talking about the amount of time it takes to compile, and we're never running a compiler here.
No, sorry, I just meant the amount of time it takes to come up with an algorithm.
Exactly. Yeah, anyway, you're absolutely right. If I deleted this I from this line, it would mean the same thing. And so maybe it's better for me to do that. Maybe it's better for me not to have the I in there. But I stuck it in there to
personally think so, because I think it just causes confusion, because if you write just I, it's just kind of, first looking at it, you can just kind of imply that it's dependent, but I guess you have to go through the an analysis of what it means, then you realize I is independent. But first looking at it,
good. You just argued for me to keep it, right?
Oh, yeah. I contradicted myself, but
yeah, because here, let me repeat what you just said. If I deleted the I from here, then you would say, yes, obviously A doesn't depend, that K doesn't depend on I because I is not here.
Yeah.
Right? But I'm not trying to teach you that the number of lines of code doesn't depend on the input. You know that already. I'm trying to teach you I'm trying to teach you logic, right? And so I want to teach you how these quantifiers at the beginning tells me that K doesn't depend on I, right? And if I remove the I from this thing here, then we wouldn't be having this discussion, and you wouldn't get the nuance that even with the I here, right? We're on the wrong one. Let's go back here. Even with the I here, that this tells me, this right here, that the K is before the I, tells me that the K doesn't depend on the I, right?
Right.
I really want you to know that because the K is before the I, that the K doesn't depend on the I.
Right. Okay.
And I want you to know that because of this, not because of this.
Yeah,
that makes sense.
Obvious. Yeah. Pretty obvious, yeah.
Well, you might say it's obvious, but people have been getting it wrong for so long. When I went, I look at this one screen and there's such a delay between the screens. Does it drive you guys nuts?
We don't have anything to compare it to, though.
Yeah, that's true. You know when I say something, but I point at something and talk about it. Here I point at the A. Here I point at something and I talk about it, and it takes a while for it to get there. In fact, I don't think my pointing is really. Here, look at my pointing. It's so slow on that computer. There, I'm pointing at the K. But it took a long time to get my mouse there. So I guess the bottom line is I think I'm pointing at things to help you understand. And you're not seeing it. Sorry about that.
Can you go back to the previous slide? No, like the last one you showed.
Oh, up here? This guy?
Yeah, so I just want to double check if I understood this correctly. You had this logic sentence here. Can I understand it as because K is the a number of lines, right? So
Right.
for any number of lines, there is a single algorithm for.
Right. Right.
There exists an algorithm for
Right.
any number of lines,
Right.
and then for all inputs.
Right. Exactly. So what does that mean?
So
Yeah.
it means that for any number of lines of code,
Right.
there's
There's an-
algorithm.
Yeah. If I
that
gave you a
computes.
number, say 1,000,000. Well, maybe 1,000,000 is big. Let's say I give you a number 108. Could you write me an algorithm that had 108 lines of code?
Yeah.
Yeah, that's all this is saying.
So
Right.
the algorithm doesn't even have to compute anything because it doesn't
Yeah.
say P.
Exactly. You're getting this completely. There's no requirement on the algorithm.
So
All
I can
we're
just
saying
write
is that
anything.
for every K, there's an algorithm that has K lines of code. Right? In fact, we can kind of go through here. What does this say? This says algorithm A on input I has K lines of code. All right, we bring this in. Well, we can say it doesn't matter the line of code. Right? The input doesn't matter, right? Again, we're saying the K can't depend on the input, right? K comes before the input. So algorithm A has K lines of code, independent of the input. And then what does this say? Oh, it says, oh, here K is the free variable. So it says K is an integer that has the property. What's the property of the integer K? The property of integer K is that there's an algorithm with K lines of code, right?
Yeah. So and the algorithm doesn't have to compute anything.
Doesn't have to compute anything. There are algorithms with any number of lines of code. For any K, you can give me an algorithm with K lines. Right? That's what it's saying.
And the input doesn't even matter in this
The
case.
input doesn't even matter, right? So this is saying something,
Okay.
right? It's just a little bit of text. It's a little bit of text, and it's in some ways it's telling me something very deep. Right? It tells me I can write my programs as long as you want, and it won't depend on the and the input doesn't matter.
So is it that all that matters though is that if the problem is actually computable or not? Like that's something you need to know ahead of time, or else none of this works.
We're going to bring problem in here in the next slide. Right here, we're not talking about the problem. We're just talking about code, right? I mean, you can imagine, suppose you're working in some company and you want to know, you're going to go to your boss and say, is there a resource limit on how many lines of code I can write? And what's your boss going to say? She's going to say, oh, no, don't worry, buddy. There's no restriction on how many lines of code you can write. For any K, you can write a program with K lines of code. Go for it. There's no restriction on K.
Right. But this tells us that assuming that it's computable, then we can get an algorithm with any size input.
No. Do you see any computation here?
I
We never
remember
ran our A.
when you did the game.
Yeah.
I don't remember where it was, if it's forward or back in the slide.
Here. Yeah, back here. Now we're talking about the algorithm running
With
and
the
solving the
P.
problem.
Yeah.
Right? So there we need it. We go forward. Right? You're getting a little ahead of us here.
Right, but does K
Now,
affect compile
now we
time?
bring in the problem being solved. Right? Here, we had this sentence here before in B, we had this. But now I added that now for every K, I have to come up with an algorithm, and it has to have K lines of code, and it has to solve my computational problem, right? So this is a harder statement.
Oh, okay, so earlier with B, we didn't have the A of I equals P of I.
We didn't have that, right? Without this, turns out this is true, and not only is it true, it's trivially true, right? It's saying something that's trivially true, and you should know it's trivially true, but and you should be able to say it. Right?
Okay.
And here I'm saying something very hard, and it'll turn out that this is false.
Oh, okay. So the A of I equals P of I means that you can make an algorithm assuming that the problem you're given is actually computable?
This right here, what does that right here say? It says algorithm A on input I gives me the required answer for computational P on input I. That's what this says. Right? Here, in fact, we can, right? What is, here we have a bunch of free variables. And what is all this saying? It's saying I have an input, I have an algorithm, some input, some K, some P. Those are all free variables. And what am I saying about them? It's a relationship between all those free variables. And it's saying on input I, algorithm A solves problem P, and it has K lines of code. Right? Now, to say P is computable, we have to talk about, well, which algorithm, which input, right? Right now, we're not saying which algorithm, which input. We're just saying whether this is true or not depends on, you have to give me each of those free variables. Right?
Right.
And even if P is not computable, there could be some algorithm that gives the right answer on some input. Right? So this might be an uncomputable problem. And this is an algorithm that just happens to give the right answer on this input. Maybe it's a computable problem and the answer is 5. Right? Here's a problem. On this input, the answer is 5. What does algorithm A do? Well, it says it output for any input, it outputs 5. The whole code is just write 5. So in this algorithm gives the right answer for that input.
So assuming that it's computable with this specific input, then the algorithm will come up with.
I would prefer that you don't say that. You're getting kind of Clockwork Orangey on me.
All right.
Right? Can we just, we're not talking here about whether it's computable or not. We're saying that to be computable is a much harder statement. All we're just saying is it just so happens that this algorithm gives you the right answer on this input.
I think I was just overcomplicating it. It's okay.
Yeah,
Thank you.
yeah, you're trying to, I mean, but that's what we do. We try to understand and we say, hey, does it mean this? And I'll say, nope, doesn't mean that. It means something else. It's all good.
All right.
So does K affect compile time, like the lines of code?
How are you? Yeah, I really got to change this word compile time. What do you mean by compile time? When you say, does it affect compile time? It sounds like you're talking about the amount of time it takes to compile. Or are you talking about the compile epoch?
Coding time.
Coding time.
Programming time.
Yeah,
so
yeah, certainly if you're going to write why didn't I ask you to write me 1 billion lines of code? Because,
compile time.
You would be sitting in the basement an awfully long time. One of the measures I do in order to give you an assignment is I write up the solution and I sort of look, how long did it take me to write up the solution? How long is my solution? Right? And it's hard for me to, right? And those aren't very good measures because you are going to take longer than me. But certainly if my solution is 10 pages long, then I know we got a problem. Anybody, any other questions?
That's all the questions I have. Thank you.
Excellent. Excellent. All right.
Sorry. So just to make sure, last time, so A of I equals P of I just means that an algorithm with the given input I will be able to solve the problem P with the same input I.
Yeah. Yeah. Yeah.
Right. So I guess the algorithm would just be
I
the
mean, even the
solver.
word solves, you say is able to solve, and I don't even like that word. I mean,
I'm
I
taking
said it here, A solves P, but solves has a bigger verb to it than I really like. Maybe I should change this to say A happens to give the right answer for problem P on input I, right? It could be that all A is doing is outputting 5 without any thought whatsoever, right?
So it comes up with an output for
Comes up
problem
with,
P.
yeah.
So that's not the same as solves?
Well, we're getting a philosophical question. Here, suppose I have a Java program and what it does is it outputs 5. That's all it does, right? Does it solve the computation problem on inputs whose answer happens to be 5? Yeah, it's a philosophical question.
Well, well, logic is a branch of philosophy, isn't
Yeah,
it?
for sure, for sure. I mean, here's a joke. Have you heard this one? If you got a clock that doesn't move, right? The hand doesn't move, then it's right twice a day. Right?
I suppose you're right. Yeah.
Yeah.
But neither does it really tell you what time it is.
Hello, Jeff.
Yeah.
So for this case, case C, so it is false, right?
Oh, C? Yeah, C is false.
Because for every input there is A, but the K for the A is unique. It cannot be for all the K, right?
No, you're getting it wrong. No, you kind of said for every input there's a K, and I don't like that.
No, for every input there's A.
No, I'm not saying that either. There's one A for every input.
Yes.
You're saying something that sounds like the Clockwork Orange thing to me.
Yeah, there's A for every input. Hmm.
If this is true, here, you can think about this I mean, you can just go to the next slide and see it, but if it's true for every K, let P be a really easy problem like sorting. All right? Sorting. Is sorting computable? Yeah, it's computable. All right. Now, this is true for every K. Let me give you K equals 2. Right? So is this sentence true for K equals true? Does there exist an algorithm that solves sorting problem that has only 2 lines of code?
No.
No. That's why it's false.
Okay, got it. Thank you.
But we're going to do that. I keep saying tomorrow, but you know it's not true. We're going to do it on Tuesday.
Sorry, Professor, but we'd be testing it based off of different inputs, right? Not based off of different Ks. Sorry, I mean you said can you find do you have an algorithm that can sort an input I in 2 lines of code? You can't,
Yep.
right? So it's false. But
It's false.
wouldn't we be focused more on the different inputs? And then from that algorithm and from that input, then you find a certain number of lines?
Now you got to come up with in here, we have to talk about the K first. And the
Okay.
adversary is giving you a K.
Mm-hmm.
Right? I'm saying, is this true for every K? Well, if you give me K equals 2, I can come up with an algorithm that has K lines of code, that's 2 lines of code, right? That's easy. Coming up with an algorithm that has 2 lines of code is easy. P is sorting. Coming up with an algorithm that solves sorting is easy. Well, relatively easy. Once you've learned quick sort or insertion sort, it's easy, right? I come up with an algorithm, insertion sort, it solves P. But coming up with an algorithm that both has 2 lines of code and that solves P, that sounds hard to me. Alrighty.
Are you saying this is false?
Yes.
But if you give like a domain for K, like say a precondition that K has to be within a certain range, then doesn't this can possibly be right?
Yeah, I mean, you can always define things to be differently. We could change the sentence. But even if I make, suppose I make P really a hard problem, even if it's a computable problem but hard, I might be able to solve it with 1,000,000 lines of code, but I can't solve it with 100 lines of code.
Okay, so if the prover is just saying, okay, you can only choose it from 1,000,000 to 2,000,000,
Right.
that's the precondition, then this statement would be right.
No, because if you're a software engineer and you go into TTC, and TTC says, I want a program that solves all the problems I have with TTC. I got to keep all the trains running. I got to keep track of the books for all of my employers, right? That's a problem that's solvable, but I forget what your range was, but it didn't sound like it was enough. You know, the software engineer is going to say, okay, great, but I'm going to have to write, I don't know how many lines of code. How many lines of code do you think TTC has to run?
Like over 1 billion.
Yeah, I can't imagine how many lines of code it has, right? Could it have written with half as many lines of code? Yeah, probably you could. Could it have written it with 100th lines of code? Maybe. Could it have written it with 2 lines of code? No.
So it depends on the problem then.
Depends on the problem. Depends on the problem. Right? I would go as far as to say another first order logic statement. I would say for every P that's computable, there exists a K where you can write a program that solves P with K lines of code, but you can't write a program with K minus 1 lines of code. Right? I would be willing to say that. Right? Every P has some minimum lines of code that you need to write. And when you're an expert coder and you go out into the world and your boss and you know you're contracting, and the company says, I want you to write the code to run TTC, you're going to have some understanding of how many lines of code that will take. So you'll have some understanding of how much you want to charge them.
Okay, thank you, Professor.
Excellent. Any other questions?
Professor?
Thank you.
What if we use a Turing machine code for this algorithm? Will this be scenario something similar to what we did for the test 2?
Sorry, so you're talking about 2001?
Yeah, like remember for test 2, I remember the question was something similar to what we are talking about here, where we had some algorithm.
In test 1, we had statements like this, first order logic statements, and I wanted you to understand them. In test 2, we actually built the Turing machine.
Yeah, but it was something similar, like the algorithms we were using from this, and then we were writing the code in Turing machine, like Turing machine code.
Yeah.
But will we do something differently if we were not using the Turing machine code in this case?
Well, in this course, we're the next slides is going to be talking about compiling from Java program into Turing machine, and we will write down the first order logic statements saying that you can do it, but we won't actually be defining a Turing machine. We won't actually be doing the conversion.
Oh, so it will be just arbitrary and proof? Like, will we be just doing it with that, or will we actually writing like a Java code?
This course is a logic course, so we will only be writing logic statements.
Okay.
Right? This is kind of like an English course in which they teach you how to write sentences in English and know what they mean. But this is a logic course, so we're going to be writing sentences in logic, and we need to know what they mean.
Okay, yeah, that makes sense.
Right?
Yeah.
And if you look at my syllabus page, right, there's so many lines of logic there, right? You scroll down, there's so many lines of logic, and I would really love to get to them all. But when we get to them, we will not be proving they're true. We're just going to be, do we understand what it says? Right? I believe that you in first year should be able to look at one of those each line of logic I have on that first page. My fantasy is you'll be able to look at it and says, what does this line say about the world? So later, each of those lines, somewhere in second or third year, you're going to have to prove it, right? And I just thought if I could prepare you so that in first year, you know what it means, then when second and third year, when you have to prove it, you'll be ahead of the game because at least you'll know what it means.
Yeah, right.
Right? Because I find I try to teach stuff in second year and third year. I want to teach that they mean what this line means, and people don't know what it. I want to prove it's true, and they don't even know what it means. And how do I prove it's true when you don't? You got to know what it means before you prove it.
That's true. Yeah.
Right?
Right.
A bunch of faces here that I've seen these pictures before, but you never turn your videos on. There's a face. I know you.
Yeah, sorry, room wasn't quite ready for video.
Yeah, you got your dirty laundry everywhere. I know about that.
Bye, Professor. Thank you for the lecture.
My room has dirty laundry in it too, but you only get to see my wall.
Yeah. You're the prof. You can teach in bed. It's okay.
It's a pretty good job where you get to teach from bed, isn't it?
Yeah, for sure.
I got my pajamas on.
Yeah.
Once I turn this off, I don't have to go far to have my nap.
Just gotta make sure you left the meeting.
Yeah, exactly. Yeah, for sure. One of these days, I'm gonna fall asleep with the video still running.
Yeah. You know what? We tried Laziza and.
Oh yeah, it's good, isn't it?
It's amazing. It's amazing.
I eat at Laziza 2-3 times a week. I mean, I don't know how I would live without Laziza.
Yeah, it's pretty good. We had the same concept in Belgium, close to my city, and but it was, I don't know. What kind of, where is that type of food from? Shawarma.
I think about it as a Middle East. So the funny thing is, both the Israelis eat it, and Pakistan and Palestine, both the sides. Chicken shawarmas come from over there.
Because what we had was it was Turkish actually. It was
Right.
called
Oh yeah, Turkish. Well,
durum.
that's Middle East.
Yeah, but the bread was it's not the little pouch that they slice in half. It's a whole, like it's a bit bigger, like a
Right.
burrito
Burrito,
type
yeah.
of bread, I would say.
Yeah.
Yeah.
Yeah,
And
exactly.
what I
Exactly.
liked about that is that they can increase the size, because sometimes from Laziza you need 2 chicken shawarmas
Yeah.
to be
Well,
full.
the plate is so much food.
Oh yeah? I haven't
Oh
tried the
man,
plate
if you
yet.
get, well, for me, I'll buy a chicken shawarma plate, and I eat it for lunch and then for dinner. It's so much food.
Okay, well I'll
Let me
try
tell
that
you,
then.
one of my favorite people is Pam. That you go a little bit further down the street, closer to the library, and it's Pam's Roti. She's a short little Trinidadian woman. She's been making me rotis since for the last, I think she's been making me rotis for 20 years.
Wow.
So you tell her that you know Jeff, and if it wasn't for COVID, she would give you a hug. She
Okay.
had her picture of me on her wall before she painted. Now it's painted green, and the picture came down. But I used to be up there.
Nice.
In fact, when she moved to that new location, I was one of her first customers in the new location, and they didn't know how to work the cash register. So they gave me the manual, and I'm trying to figure out how to use the cash register while customers are coming in. And so I'm selling them rotis as I'm trying to figure out the cashier.
That's funny.
Yeah. And then Bajara's is down at Christie Pitts.
How do you spell this one?
Oh, how do you spell Jeffrey? Banjara, B-A-N-J something. It's at the corner of Christie Pitts. It's Indian food.
Okay. I'll look into that too, because it's nice to have little recommendations that are around the place that you can bike or scoot there quick.
Exactly. Have you been
Yeah.
down to Chinatown and down to Kensington Market?
No, not so much yet. We've been buying food from the grocery store, and
Right.
and it's just when we don't have food that Laziza.
Right, exactly. I lived in Belgium for a year.
Nice. Where?
Yeah, I loved it.
Where about?
We lived in Louvain.
Louvain, nice. So you were there for the university?
Well, I was 12 at the time.
Oh, okay. So not for the university.
No, not for me. Oops.
With your parents? Oh, you cut out. I think. Yeah, we cannot hear you. You have to unmute on the second computer.
Yeah, it fell down. Are you back? There we go. Yeah, my father is a math professor, and he was doing a sabbatical in Louvain, and I was 12.
Okay. Yeah, Louvain is it's like Kingston, but much closer to bigger cities.
Right,
It's
exactly.
City built around a university. Yeah. And I would say it's also nicer than Kingston. Louvain is a much newer city compared to the rest of Belgium. So, and it's mostly, I don't know if it was already like that. Sorry.
I met the nicest people. I was 12 and I had this really, really nice 16-year-old female friend. She wouldn't let me kiss her, but we had a lot of fun together.
Was it a friend from school?
She was Flemish, so they didn't want to send me to a Flemish school. We went to a really bad French school.
Oh, French, okay.
But I didn't learn any French, so I stayed home and did correspondence courses.
That must have been rough.
No, I loved it.
But the French school.
The French school was pretty rough. They made us copy off the board without any understanding, and the people were all pretty mean. The French school was pretty bad, but the Flemish friends were really, really good. I hope you're Flemish and not French.
I'm French.
Oh, you're French? All
Yeah.
right, well.
But I used to know my Flemish from doing all my sports camps in the Flemish part, because my dad really wanted me to learn the language, and the Flemish culture part of the Flemish part of Belgium is more strict and rigorous than the French part, who is a little bit like a bit more lazy, you know. And it's comparable, like it's like we're French and the North is either Dutch or German, you know, but there's a big contrast of general attitude. And yeah, I felt that a lot when I went to Flemish camps as the only kid in French. It was rough. It was rough.
Yeah, I can believe it. Yeah, my friend studied 6 languages in school.
Studied?
Yeah.
Nice.
It was required. Hey, here's a question. Do you go? You're with your lips. You go. Do you do that?
What?
When I was in Belgium, all my friends did it.
What?
It just means, I don't know.
Buff?
They kind of, you kind of put your blow out of your mouth. Anyway, that's what we did when we were 12 in Belgium. I thought it was a Belgian thing.
Maybe. I couldn't know. I mean, I grew up there pretty much.
Yeah.
But yeah, no, it's nice. It's definitely good, you know, to be able to be exposed to different cultures, because they're not just, you know, like everyone.
Exactly. Yeah, I was in Munich for 4 months. I was in Africa for 8 months. I was in India for a year.
For your
been to Thailand 3 times. I travel a lot.
Was that for as a child with your
Sabbaticals.
parents?
No, Munich was